Hello, everyone, and welcome to the latest lecture. So today we're going to be talking about mostly 5.5 stuff. I just want to start with a quick note on some properties of the integral that are very important. Okay. So two of the key properties of the integral that make life a lot easier for us is this property, this first property. If I have the integral of a f of x dx, and a is a constant, I can pull that constant outside my integral. Okay, so I'll do an example real quick. So for example, if I had the integral 3x squared dx, I can pull this constant 3 outside my integral and say, well, that's the same thing as 3 integral x squared dx. Okay. And in the same vein is this second property that if I have f of x, the integral of f of x plus g of x, well, I can split that up into two separate integrals, the f of x, integral of f of x plus the integral g of x. So these two properties combined give us a lot of power in integrating simple expressions of functions. So for example, if I had the integral of 3x squared plus 4 sine of x here, well, I could first start by splitting this into two different integrals. Integral of 3x squared dx plus integral of 4 sine of x dx. And then I could bring each of these constants outside my integral equals 3 integral x squared dx plus 4 integral sine of x dx. And then evaluate those integrals individually and then put them back together. And I would only need one constant of integration. I don't need a constant of integration for each indefinite integral. So why is this important? Well, we usually kind of skip these steps. So if I had x to the fourth plus 7x plus cosine of x, okay, I can just integrate these pieces individually. And I oftentimes don't bother splitting up this integral into pieces. You know, I could split this up into three different integrals and then integrate those things individually. But really, as long as I know that this property holds, which it always does, I can just go ahead and integrate this all in one shot. I know the indefinite integral of x to the fourth is x to the fifth over 5. I know the integral of 7x would be 7x squared over 2. Integral of cosine of x should be sine of x. And then I add a single constant of integration. Okay. So I can, when I have an integral of several things added up, I can either split that up into several integrals or I can integrate it all in one shot, whatever's more convenient. However, there's some stuff we can't do with integrals, all right? So for example, we can't split up f of x times g of x, okay? So if I have this integral f of x, integral of f of x times g of x dx, that is not equal to the integral of f of x times the integral of g of x. And a lot of, here's an example of us trying to use that. So if I had a function, the integral of the function sine of x cosine of x, that is not equal to integral of sine of x times integral cosine x dx. We're going to see how to deal with this by the end of the video. Okay, how do we deal with this situation? Well, there's going to be several different methods we use, and that's what a lot of this course is. A lot of this course, a lot of the sections in this book are overcoming this difficulty, this one function multiplied by another and trying to integrate. So there's a lot of techniques, and that's what a lot of this textbook is about. And in section 5.5, we're going to learn a specific technique, the first tool in our toolbox of integration. It's going to be the u-substitution. Okay, so let's go over the u-substitution for indefinite integrals first, and then we'll see the case for definite integrals a bit later. Once we learn how to do indefinite integrals, doing it for the definite integral is just adding a single easy step. Okay, so to motivate this tool, this u-substitution, remember the chain rule from Calculus 1. If I started with this f of x, f of g of x, this composition of functions, and I wanted to take the derivative of that, remember what that would be by chain rule. It would be f prime of g of x times g prime of x. Okay, and then if you guys remember the fundamental theorem of calculus, if we have some nice conditions on our functions, then the integral and the derivative should basically just cancel each other out. So I naively expect that, okay, if I just integrate both sides of this thing, okay, if I look at that expression and just integrate both sides, what's going to happen? Well, in this, on the left side, the integral and the derivative are going to cancel out, and then I have the integral on this side. So I expect to get this line. Okay, when I integrate something that looks like this, f prime of gx times g prime of x, well, the antiderivative of that should be just f of g of x. Okay, so that's the motivation behind this u-substitution. Now that's just an idea of what's going on. We need to really kind of firm up our understanding of when to use this and how to use this. So let's first talk about when to use this, and then we'll talk about how to use it and how it actually works in practice. Okay, so let's talk about when to use it first. So let's say I have the integral of f of g of x times g prime of x. So this is a little bit different than what I had above. In the above lines, I had something like f prime of g of x times g prime of x dx, right? Now I just have this, instead of having f prime, I just have this function. Okay. Don't worry about that. That's just a small distinction. It's all going to work out in the end. The key here is that this f, we're going to try and find, we're going to try and make a substitution, and then we're just going to integrate the function f, right? So that function hopefully has an antiderivative we can find easily. Okay. But when do we use this technique? When I have an integral that's in this layout, f of g of x and g prime of x dx. Okay, so what are these pieces? This piece here, this piece right here, I have a sort of nested function. I have one function inside of another, right? I have g of x inside the function f. And then that whole thing is being multiplied by the derivative of g. Okay, so I need to be able to recognize that situation. So a quick example over here in the corner would be, let's say I had square root 1 plus x squared, right? So what would be my f? What would be my g? Okay, let's see. So this is the square root function, right? So we could say f is square root, and then what's inside my square root? Well, 1 plus x squared, okay? And then let's say I had 2x out here, well then 2 of x would be my g prime. Right? Okay, so I need to be able to spot this situation. So if I was given this line here, I know my f would be square root, my g would be 1 plus x squared, and my g prime would be 2x. Okay, so that's the situation when we use this method. Okay, and then just some examples that I want to use to illustrate a couple points. First of all, order doesn't really matter, right? It can be, let's see, if I was looking at this top example here, well, what would be my nested function? Well, I can see this thing has one function inside of another, right? So what would be my f, g, and g prime in this case? Well, f would be the square root function again. G would be my 1 plus x cubed, and then g prime, well, that would be 3x squared, right? And now in this case, the 3x squared is out front instead of in the back. That doesn't matter at all. And actually, we can loosen our restrictions on the g prime a little bit, right? it doesn't have to be, this g prime doesn't have to be exactly the derivative of what's inside. It can be different by a constant. So that is displayed in this second example. Okay, let's look at the second example here. Okay, I've got one function inside of another. Okay, so f is 1 plus, oh, excuse me, f is just the square root function. G is the stuff inside the square root function, 1 plus x cubed. And then what do I have? What's left over? This should be my g prime, but let's see, g prime should technically be 3x squared, right? And instead of 3x squared, I got 17x squared. But that's fine, as long as it's only different by a constant, meaning just a number like 17, 4, 1/4, 0.007. It doesn't matter as long as it's just different by constants. We can still use this method. Okay, so those are the points I want to illustrate. That order doesn't really matter, and the g prime can be different by a constant. Okay, so in those situations, we can still use the u substitution. Okay, and that's what I've stated here. If derivative part is different by a constant, that is okay. Okay, so that's when to use this method. Let's talk about how to actually use it. So in the previous explanation, we said, okay, well, if I have this chain rule thing, and I integrate both sides, okay, here, oh, here the integral and if I integrate both sides, the derivative and the integral are going to cancel out. And I should have the integral of this right side is just equal to this left side, okay? The problem is when I'm applying this method, I don't usually know what f is the derivative of, okay? So f is the derivative of some function, but I got to figure out what that function is, okay? So we're kind of starting from here where we don't really know what f is the derivative of. We don't know what the antiderivative of f is. Okay, so that's really the problem in integrating this. Okay, if we knew what f was the derivative of, we could do this all in one step. Okay. So let's say we're starting from this problem. We're trying to integrate f of g of x times g prime of x dx. The first, what we want to do is we want to substitute a value in for g of x. That's going to make this easy to integrate. All right, so we're looking to use some sort of substitution to make this just an integral of f, basically. All right, so we're going to say, we're going to replace g of x with just a simple variable u. Okay, so hopefully at the end of my substitutions, I'm going to end up with just an integral of f of u of du. Okay, so just a much simpler integral. All right, so I want to replace g of x with u. But if I replace g of x with u, I also have to change dx. I can never have in this course, we're never going to have an integral that looks like this where I have f of u dx. Okay, I can't have one variable inside my function and integrate with respect to another variable. Okay, that's going to be different when you get to Calc 3. But for Calc 2, for this course, if I have u's inside my functions, I have to have du's here. Okay, so if I'm replacing g of x with u, I also have to replace dx with some stuff. So how do I figure out what to replace dx with? Well, starting from this line here, I'm basically going to differentiate both sides, okay? But it's a little bit different notation than just finding derivatives. I'm going to go from u to du, okay? So when I think about this, I'm sort of differentiating both sides of this equation, but instead of writing u prime or d over dx of u or something like that, I'm going to differentiate u and turn it into du. Then I'm going to differentiate this side as well, this right side. So what does this right side become? This right side, since I have this function of x, well, its derivative would be g prime of x, and then I'm going to tack that dx onto the end, okay? And now what I'm going to do is I'm going to solve for dx, okay? I want to get dx by itself. So how do I do that? I just divide both sides by g prime of x. So I see that if I do the substitution u equals g of x, that gives me this substitution for dx. dx is going to be equal to du over g prime of x. So figuring all this stuff out is my first step. Step 2 would actually be plugging this stuff into my problem. Okay, so this is my original problem. I have the indefinite integral of f of g of x, g prime of x, and I figured out what my substitutions were in step 1. So now I'm gonna go ahead and make those substitutions. I'm gonna replace g of x with u, and I'm gonna replace d of x with this stuff, du over g prime of x. Okay, so now I'm here. Step 3, let's just simplify everything. Okay, the first thing I want you to notice is we have a g prime of x here, and then we're dividing by g prime of x. So those should cancel. All right, and going back to what I said earlier, that this doesn't have to be exactly g prime as long as it's only different by a constant. Okay, if we have that case, maybe we'll have some constants left over. Maybe we'll end up with, well, we'll see that in some later examples, but maybe in this step, we're going to get some constants like 1 over 4 or 7, something like that. Okay. So next step, after we've made our substitutions, is just to simplify. So as I said in the previous step, we have g prime of x, and we're dividing by g prime of x. Those cancel out. And once those cancel out, I'm just left with the indefinite integral of f of u du. Okay. So now, if this function f is easy to integrate, I'm in good shape, right? I can if this function f is easily integrated, I just integrate it in terms of u. Okay, and I end up with some antiderivative, capital F of u, and then I add my constant of integration like I do with all indefinite integrals. Okay, and then the last step, since I started with integrating a function of x, I want to end with some function of x. So how do I get back to a function of x? I just undo my substitution. Okay, so let's go ahead and see an example. This stuff is usually hammered home when we see this in action. So let's look at the integral, in the indefinite integral 3x times square root 1 plus x squared, or 6x squared. Okay, so the first thing to do is identify our substitution. So where's my nested function? Where's the one function inside the other? Well, that would be here, right? So my f would be square root, and then my g would be 1 plus 6x squared, right? So I want my substitution to be u equals g of x, so I want u equal to 1 plus 6x squared. Okay, so that's my substitution. Once I know that, I can differentiate both sides, my sort of pseudo differentiation. I'm going to differentiate both sides. My u becomes du. What's the derivative of 1 plus 6x squared? That would just become 12x, and then I have a dx on the end. And then I'm going to solve for dx by itself. So I get du over 12x equals dx. Okay, so again, this is one of those cases where the stuff we're multiplying by, this isn't exactly g prime of x, right? But it's only different by a constant. G prime of x would be this thing here, 12x. So instead of 12x, I have 3x, but that's fine. It's only different by a constant. Okay, if I multiplied 3x by 4, I would have my g prime of x. So it's only different by a constant. All right. So we figured out our substitution. Our u should be 1 plus 6x squared. Our dx should be du over 12x. So let's go ahead and make our substitution. Okay, this is my original problem here on the left. I make my substitutions. We'll leave 3x where it is for now. I replace the stuff inside the integral with just u. And then I replace dx with du over 12x. Next step is to simplify. Okay, I got 3x here, and then, let's see, I got 3x where? I got 3x right there, and then I'm dividing by 12x there. So let's put those terms together in this line. I got 3x over 12x, and then I got square root u du. Okay, simplifying further. Well, 3x over 12x, that's the same as just 1/4, right? That constant, I can pull that 1/4 outside my integral, and then I just have the integral of u to the 1/2 to the power of 1/2 du. So remember that square root of u is the same thing as u to the 1/2. Once I have it in this form, it's clear that when I integrate, I should use that power rule, right? So when I integrate, what do? I add 1 to the exponent and divide by that number. So I get u to the power of 3/2 divided by 3/2. And then I have my constant of integration out front, or excuse me, out back. And then it's just simplifying. Okay, I got 1/4 u to the 3/2 over 3/2. Well, when I divide by a fraction, that's the same as multiplying by the reciprocal, right? So I have 1/4 times 2/3 u to the 3/2 plus c. Okay, simplifying that fraction out front, it becomes 1/6 u to the power 3/2 plus c. And then at this step, I'm pretty much done integrating, but since I started with a function of x, I want to get it back to a function of x, right? So go all the way back to our original substitution. We had u is equal to 1 plus 6x squared, right? That was our original substitution. Now, since we have an integral in terms of u, let's undo our substitution and replace u with that, okay? So I've replaced u with 1 plus 6x squared. It's still to the power of 3/2. And then I have the 1/6 out front and the c in the back. And I'm now at this stage, I'm done. This is my indefinite integral. That's my solution. So that covers the case of indefinite integrals. And again, I'll do a problem video for this section where I do several more examples. Let's just cover the theory now for definite integrals. So the good thing about this for definite integrals is it's virtually the same as indefinite integrals, just maybe with one small extra step. So we have the same setup. We have integral. This time we have bounds from a to b. We have an integral from a to b of f g of x g prime of x. So here's kind of an idea. This is kind of how I think about these u substitutions. Okay, so over here is, let's say we're integrating this function f of g of x g prime of x. Think about what that would be intuitively. I would find the area between a and b for this curve down to the x-axis, right? That's pretty much what my integral is. On the other hand, to make this a bit simpler, okay, I could think of this as the integral of f of u. And instead of integrating down to the x-axis, I'm just integrating down to this function g of x. Okay, this intuitive idea, it's not too important. If you just memorize the mechanics of it, that's fine. But this is kind of how I think of it. But if I'm integrating down to a different axis, then the points I'm integrating between have to change, right? So in my original, I'm integrating from A to B, okay? But now in this new case, I don't have A and B, right? Well, what do I have that are kind of the same? I have G of A and G of B. So those should be my new bounds of integration. So if that doesn't make sense to you, if you don't want to deal with that, just think of this short story. Keep this in your mind. If the bounds of my original integral are a to b, and I'm saying that my substitution is u equals g of x, then I need to have new bounds on my integral once I make my substitution, and those bounds need to be g of a, g of b. Once there is a small idea I want to mention now, and we'll see it at the end, but once we change our bounds, we're going to have a choice of whether or not to undo our substitution at the end. But let's go through this step by step. So in this symbolic notation, I'm starting with the problem, the integral from a to b of f of g of x times g prime of x dx. Step one is still the same. I figure out my substitutions. Okay, so maybe this is what we've done before on this left side. Okay, so we figure out our substitutions in terms of u and du. And then over here, we could also figure out, we could also change our bounds. So if we're saying u is equal to g of x, then my bounds go from a and b in my original integral to g of a and g of b. Okay. Next step is to make the substitution. So I make my substitutions everywhere. I'm going to replace g of x with u. I'm going to replace this with I'm going to replace dx with du over g prime of x. And then I replace my bounds a and b as well. Okay, and I get this thing. I get the integral from ga to gb of f of u du. Step 3 and 4 are the same as in the case for the indefinite integral. We simplify and then we integrate in terms of u. In step 5, we have two choices. Okay, since I've changed my bounds, okay, once I've integrated in terms of u, I could just plug those new bounds into my antiderivative f, capital F of u. Or I could undo all my substitutions and use my original bounds. So again, maybe this doesn't make sense to you, but let's see an example real quick for this definite integral. So let's say I'm integrating from 0 to 1, the cube root of 1 plus 7x dx. Okay, this might be a little confusing because we have this nested function, right? But we don't have it. Where's our g prime of x? There's nothing out front or out back of this nested function, right? So does this fit our format? Well, first, let's ask ourselves what our g of x would be. Okay. Well, g of x would be the 1 plus 7x, right? That's the stuff inside my nested function. Well, then what would be g prime of x? Well, g prime of x would just be 7. Okay. Well, do I see a 7 anywhere? No. But I could say that this function inside my integral, okay, that's the same as 1 times my function, right? If I multiply it by 1, then it's not changed at all. It's the exact same thing. Well, is 1's not equal to 7, but they're only different by a constant, right? So it's like I have a g prime of x out front, but it's different by a constant. So we can still use our method. So now let's continue through our steps. I'm saying u is going to be my 1 plus 7x. My du is going to be 7 dx. And then solving for dx, I see du over 7 equals dx. How would my bounds change? Well, remember my gx is 1 plus 7x. So if my original bounds are 0 to 1, I want my new bounds to be g of 0 and g of 1. Well, what's g of 0? Plug in 0 into g of x, I would get 1. What's g of 1? Plug in 1 in, I would get 8. So my new bound should be 1 to 8. Okay, let's go ahead and make our substitution. So here is my original integral. I make my substitutions and I get this. Okay, I got du over 7 and then cube root of u. Let's go ahead and simplify. I bring the 1/7 outside, and now I have the definite integral from 1 to 8 of u to the power 1/3. Remember, cube root of u is the same as u to the 1/3. Okay, now this is easy to integrate. I just add 1 to the exponent and divide by that number. So I have u to the 4/3 divided by 4/3, all times 1/7. And then I should put a bracket with my bounds, my new bounds on the right side, just to indicate that I know I'm going to be evaluating this antiderivative along my bounds. Okay, so simplifying my antiderivative, I got 1/7 u to the 4/3 over 4/3. That's the same as this. Okay, 3/28 u to the power of 4/3 from 8 to 1. Okay, so now we've found our antiderivative, and in the indefinite integral, what did we do? We undid our substitution, right? In in step 5, we have this choice of whether to undo our substitution or not to undo it. Okay, so let's look at 5a first. Okay, so I have this antiderivative and I got these new bounds. Okay, well, I can plug these bounds directly into my antiderivative of u. Okay, I just plug these numbers in and evaluate it, and that should give me my correct answer. So I plug in 8. So I do 3/28 u to the 4/3, u to the power of 4/3. So I plug in 8. Okay, what do I get? And then I subtract what I have when I plug in 1. Okay, so that's this. I'm going to pull the 3/28 out front, and then I would have 8 to the 4/3 minus 1 to the 4/3. Well, 1 to the 4/3 is just 1. What's 8 to the 4/3? If you have trouble doing that, just think about it step by step. Let's go to a new page for a moment. What's 8 to the power of 4/3? Well, I could do, usually what I do is I do the denominator first, because that's going to give me a smaller number. Okay, so I ask myself, well, how I think about this is the same as 8 to the power 1/3 to the power 4. Okay, so what's 8 to the 1/3? What's the cube root of 8? Well, that would just be 2. So then I have 2 to the power 4. What's 2 to the power 4? That's 16. Okay. All right. So that's what we're doing in this step. So 2 to the 4th is 16. 16 minus 1 is 15. So I should have 3/28 times 15. And then just simplifying the fraction, I would get 45/28. Now let's see how I could have arrived at the same answer using the other method. So in this case, I've chosen to undo my substitution. Okay, so I have 3/28 u to the 4/3 with my new bounds, but instead of evaluating at these new bounds, I'm going to go ahead and undo my substitution and get everything back in terms of x. So I undo my substitution. I remember I said at the beginning u was equal to 1 plus 7x, so I'm going to plug that back in. And then if I undo my substitution for u, I want to undo my bounds and use my original bounds, 1 to 0. Well, then plugging in 1 and 0, I would end up with pretty much the same thing. Plugging 1 into this, I would get 8, and then I would have 8 to the 4/3. Plugging in 0 to this, I would get 1 plus 0, so 1 to the 4/3, so I'd end up with this. And then this is the same thing I had over here, right? So I'm going to end up with the same exact answer. I've just skipped some steps here in this ... Skip the simplification. Okay, so we have two choices. Why did I bother showing you this? Why would you change the bounds only to undo that substitution at the end? Well, if we're careful, there's a little shorthand way that I use that we can avoid changing the bounds at all. Okay, so here's how I approach these problems. Let's say I had this integral, this definite integral from 0 to 1 of x e to the power negative x squared dx. Okay, this is a u-substitution problem. So if I was doing this the way I just showed you, I would find out what my u is, all my u-substitution stuff. Okay, That's what I've done here. And then I would also figure out what my new bounds would be, right? But how I usually do this is I just skip this step entirely, okay? And let's see how that plays out. So I just kind of leave my bounds blank here. I don't put new bounds in. I don't bother finding my new bounds. If you don't want to leave it blank, and maybe this is a better way to do it, you could symbolize this by doing, let's see, our bounds were 1 and 0. We could say g of 1 and g of 0. This to me says, okay, I know I'm supposed to be changing my bounds, but I just am too lazy to do it. That's kind of my usual state. I usually am just too lazy to change my bounds, figure out what my bounds are. Okay, so I do my u-substitution. I don't worry about the bounds. I just change the stuff inside the integral. Okay. And once I make my substitution, I get this 1/2 e to the negative u du. I pull my 1/2 outside. I integrate this thing. And my antiderivative should be negative 1/2 e to the negative u. And I should be evaluating that at my new bounds. But again, I didn't bother finding out what my new bounds are. Now I'm just going to undo my substitution in the last step. So I said u is equal to x squared. So I'm just going to plug that u back in. Okay. And now once I undo my substitution, I can use my original bounds. So I'm just going to evaluate this using my original bounds of 0 and 1. So I plug 0 and 1 in, and I get this answer. So if you don't like changing the bounds, you can just remember that you have to undo the substitution at the end. So there's a couple different methods for solving these definite integral problems. Okay, that's all I have for this section. I know I maybe went kind of fast for some of you guys, but I will do a problem video with lots of examples on working these problems. I almost forgot that I wanted to go back over one of our early examples, which was this. Let's say I wanted to integrate sine of x times cosine of x dx. This is a good example because it shows that this format I gave you earlier, where I have a nested function and then the derivative outside, this is a guideline, and that's often when we use the u-substitution, but that's not the only case. So in our top line, this is another case when we can use the u-substitution, and it doesn't seem to fit this format, right? We have one function multiplied by another, but it doesn't seem like we have any kind of nested function, but it's still going to work out. And once we're done going over this, we'll maybe kind of state a more general guideline. So let's try and use u-substitution on this problem, see what happens. And we could actually do this two ways. We could do u equals sine of x or u equals cosine of x. And it's going to seem like it's going to give us different answers, but those answers are in fact going to be equivalent. So let's stick with this first u-substitution. Let's say u equals sine of x and see what happens. Let's just go through our u-substitution steps. Okay. This would be my substitution information. So this would be step 1, right? Step 2, I'm going to plug all that stuff in. So this sine of x, cosine of x dx, that's going to become, let's see, u cosine of x du over cosine of x, right? Step 3 would be simplifying. Okay, when I simplify, these cosines are going to cancel. I just have the integral of u du. That's a pretty easy integral, just power rule. All right, so I integrate easily. And then my last step for the indefinite integral would be to undo the substitution, right? Boom, and I'm done. So I get a nice simple answer. And my original problem wasn't in that f of g of x, g prime of x format. okay? So maybe a more general guideline is I should use this method when, let's see, my u is going to give me, my u leads to this differential, that's going to give me a cancellation. So in this case, okay, my u was sine of x, and then my dx was replaced with du over cosine of x. So my cosine is eventually going to get canceled out. Okay, so maybe that's more of a general guideline, but it just so happens that this is often going to be the case when we have f g of x, g prime of x. So keep an eye out for stuff of this form, because when we have something like this, we can almost always use u-substitution. And most of our u-substitution problems are going to be in this form. But just recall from, just think about this sine of x, cosine x example, that it's not always 100% of the time going to be something that looks like that. Okay. So let's see, we got, when we did u equals sine of x, we got this answer. Okay. Let's go back to our original problem and let's try that. This is just something interesting. Let's try that same problem with u equals cosine of x. Okay. Then du would be equal to negative sine of x dx, and du over negative sine of x equals dx. All right, let's plug this stuff in for our, so this is step 1. Step 2, let's make our substitution. Okay, now I end up with this integral. Let's simplify in step 3. Now, let's see, the sign is going to cancel with this sign, but I have a negative sign, okay, which I can think of as a -1, which I pull out front. Okay, as long as I keep this in mind, I don't have to write that 1. I can just leave it as a negative sign. Okay, integrating this, I get negative u squared over 2 plus c. Undoing my substitution, now I got negative cosine squared of x over 2 plus c. Okay. Now, remember when I did it the previous way, I had a different answer, right? I had positive sine squared of x over 2 plus c. Well, it turns out these two things are actually the same. Why? Because we have this identity, right? Sine squared of x plus cosine squared of x equals 1. So let's see. If I subtract, let's get sine squared by itself. Actually, let's get cosine squared by itself. So cosine squared of x equals 1 minus sine squared, right? Okay, and let's see, what about negative cosine squared? If I multiply both sides by -1, I'll get this. Okay, so now let's replace negative cosine squared of x with this in this expression. Okay, this is going to be equal to sine squared of x minus 1 over 2 plus c. Splitting that up, we get this. Now, this is a constant, and remember this c is standing for a constant, right? And it's actually standing for the fact that if we have a function, we could add any constant to it, right? So let's just absorb this negative 1/2, this minus 1/2 into this c. And if we want it to be, we could say it's equal to sine squared of x over 2 plus d, where maybe d is some slightly different than c, but it's still just a constant, okay? So this is completely the same as this guy, all right? So these two answers, even though they may look different, are actually equivalent. Now, the question is, are these the same when we do a definite integral? Well, why don't you try that out? Why don't you try integrating, sine of x times cosine of x, let's say from 0 to pi over 4. And why don't you try it both ways? Why don't you try u equals sine of x and u equals cosine of x, and see if that gives you the same answer when we have a definite integral. And it should. All right, I think I'm actually done now, so I'll see you next time.